Hello calculus students and general seekers of truth. Welcome to the continuing video here on the second part of the fundamental theorem of calculus. And in this video we're going to tackle some more challenging and difficult problems. So the first of which being, I have g of x is equal to this integral defined as from some constant a to some variable x, and I want to find g prime. Now if you look at the previous work that we did, one thing that we did in the previous example was we took the antiderivative of this thing and then plugged in 5 and plugged in x. But this is going to be a trap if you try to do it here. Okay, so in this case we cannot find antiderivative for sine of t squared dt. Okay, you can certainly try, but this is a famous example of a simple function that really has no simple antiderivative. So rather than trying to find the antiderivative, just use FTC2. Okay, so just use the second part of the fundamental theorem instead. And using that second part, it tells us that g prime is simply f of x, where this function in here, the integrand, is f. Well, so that means g prime then must be the sine of, and we can just replace t with x, sine of x squared. And that's it. That's all there is to it, to this function. And you can see that the beauty of this theorem is that it allows us to find the instantaneous rate of change of certain integrals without having to actually find the antiderivative, especially in the scenarios when no such antiderivative is easily found. Okay. Now we're going to use this same concept, and we're going to do this with the next one. Now I want to point to an important fact here, that the upper bound of this is not x, is x squared. Okay, so in this case FTC2 does not apply, at least not directly. Okay, because if you look at the definition of the explanation of the second theorem, the second version of the fundamental theorem, this statement here only works when the upper integrand, the upper bound of the integral is x. Okay. In this case, we have x squared. Okay. So we have to try some other ideas and get a little bit more creative with this. So to get more creative, quote unquote, is actually not creative at all. Cosine of t here actually does have an antiderivative. So we can use that fact to help us. So g of x is equal to the integral from a to x squared of the cosine of t dt, and the antiderivative of cosine is sine. So this is the sine of t evaluated from a to x squared. And so we can make the substitutions. This would be the sine of, just plugging in x squared for t, minus the sine of a, where a is some constant. So now we can find the derivative of this, which is equal to the cosine of x squared times the derivative of the inside function, which is 2x, plus 0, because this is a constant. Okay. And that's g prime. So that's really nice and straightforward, because we have this function that has the antiderivative. Now let's throw a monkey wrench into this process, and let's look at the third example. So the third example combines the results of the first two, or the difficult parts of the first two, namely that we have a function here that does not have an antiderivative, or not, at least not a simple one, and we have something up here that has that is where the FTC2 does not apply. So first problem, couldn't find the antiderivative, but we could use the FTC. Second problem, can't use the FTC, but we could find the antiderivative. Third problem, can't really do either one of those. Okay? But we can use the existing problems as a way to help understand the third problem, the new one. So let's look at the result of the second problem here. And if you notice something here, cosine of x squared, that's kind of like this, except that you've taken x squared and you plugged it in here. And 2x here, 2x, this is really just the derivative of x squared. Okay? So what was really happening here was that the chain rule seemed to be at play. So I'm going to solve number 3, and then I'll explain this to you as to why I did things the way I did it. So for number 3, we're going to declare another function. Make a new function. We'll call this big F. Big F of x is the same thing as g of x, except that instead of going from a to x squared, it's going to go from a to x, and we're going to use the same integrand as what we did before. Okay? So the FTC2 does apply, and we have that f prime is just equal to sine of x quantity squared. Okay, so that's really nice. Okay. Now we're going to use f to help us find g. So we are going to rewrite g using f. Big G using big F. So g of x is really f of x squared. Okay. You look at the original problem that we had here. G of x is the integral from a to x squared, but that's the same thing as taking x squared out of big F. Let me say that again. That's the same thing as taking x out of big F and substituting x squared into it. So g is the same thing as f of x squared. So that means g prime, if we take the derivative of both sides and we just use the chain rule here, this will be f of f prime of x squared, the derivative of the outside function, times the derivative of the inside function. Okay. And now we can make the substitution. Remember that f prime is sine of x squared, so this is sine of something squared. Alright, so we have g prime of x is f prime of x squared times 2x. So I've written out the same thing except for except that I've replaced f prime with this expression because that's the meaning of f prime. So now I'm just going to plug in x squared to this. So this gives us sine of x to the fourth times 2x. So the main idea is, of course, that we try to do a new problem with some complications by applying what we've seen from the previous problems. And you can see how this idea also applies to the solution to number 2. If you think about number 2, all we really needed to do was take x squared and plug it in here, and then multiply it by the derivative of that term, of this upper bound of the integral. So here, g prime, if we're trying to do this, all we really needed to do was take, sorry, for number 3, all we really needed to do, let me come, is take this x squared, plug it in for t, and then multiply, so that would give you x to the 4th, because you have t squared here, and then multiply it by the derivative of the upper bound. Okay. So I'm going to leave it up to all of you to answer number 4 and 5 on your own, as a way to just to practice and get the hang of doing this. Thank you for watching, and have a wonderful day.